Here we have a set of vectors from R2. So the set S has 3 vectors from R2 in it. And I want to talk about the span of S. The span of S is the set of all linear combinations of the elements of S. So it's the set of things that look like a scalar multiple of 1, 2, plus another scalar multiple of 2, 4, plus another scalar multiple of -3, -6. So that's a linear combination of those 3 elements in S, and A, B, and C are real numbers. It can be any real numbers. So if you think about this, it should be fairly clear to you that the span of S is closed under scalar multiplication because if you take something that looks like this, which would be something from the span of S, and you multiply it by a scalar multiple, like say D, so if you took D times this whole thing, you'd get AD times this vector, BD times this vector, CD times that vector, and it would be in the span of S because it would be a linear combination of those 3 things. And it's closed under vector addition. Because if you take 2 things that look like this, so A times 1, 2, plus B times 2, 4, plus C times -3, -6, plus something that looks like that, like D times 1, 2, plus E times 2, 4, plus F times -3, -6, you could mess around with the algebra and that would be another linear combination of those 3 vectors from R2. So we have this span of S, which is a subset of R2, that's closed under scalar multiplication and vector addition. So the span of S is a vector subspace of R2. So, because that's the subspace test, we need a subset of a vector space that's closed under scalar multiplication and vector addition. Okay, so if you have any subset of vectors from a vector space and you take its span, you're going to get a vector subspace. Now if we look at the matrix, whose rows are built 1, 2, 2, 4, and -3, -6. So the rows of this matrix, I'm going to call this matrix M for matrix. The rows of matrix M are just these vectors from the set S. So the span of the rows of M is this same vector space as the span of S. It's a vector space and it's called the row space of M. Now if you look at this set S, or you look at the rows of M, we have a lot of dependence there, because if you just take that one vector, you can get this one by multiplying this one by 2. You can get this one by multiplying this one by -3. So this is a dependent set. So what we'd like to do is find a basis for the row space of M. And so a basis is a set that is linearly independent and spans the set. So we want to find a set that's linearly independent and that spans the span of these rows. So we want to be able to get all the linear combinations that look like this. And so what you do, we're going to row reduce. So this is something we've been doing since the beginning of the semester. And if you row reduce this matrix, the first row is going to stay the same. You're going to do this minus 2 times that's going to give you zeros. This minus 2 times that's going to give you the zeros. And so you take the non-zero rows. And that'll give you your basis. So the set that just contains 1, 2 is a basis for the row space of, we call it M. So, and it's also a basis for the span of S in that example. So the dimension of the row space of M is 1, because the basis just has one vector. And so, and the dimension of the row space is called the rank of M. So the row space is the span of the rows. You want to find a basis for the row space, you row reduce, and you take the non-zero rows, and those vectors will build your basis. And then the dimension of the row space is called the rank, and you can get the dimension of the row space by looking at how many vectors are in the basis for the row space. So let's look at a bigger matrix here. So here we have a 1, 2, 3, 4, 5 by 4 matrix. So the rows of A are vectors from R4. So the row space of A is a subspace of R4. Let's find a basis for the row space of A. So what you'd do here is you'd row reduce, which I did ahead of time, so I'm just going to plunk down the answer here. 1, 0, negative 2, 0. 0, 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0. So if you row reduce this thing as far as you can, this is the matrix you'll get. And so the set containing the vector 1, 0, negative 2, 0, and 0, 1, 1, 0, and 0, 0, 0, 1 is a basis for the row space of A. And so what is the rank of A? The rank of A is the dimension of this row space, which is the number of vectors in the basis, which is 3. And so we can find the row space, a basis for the row space, and you should understand the idea of the row space, and you should be able to find the dimension of the row space, which is called the rank. Okay, so that's rank and row space of a matrix. Okay, very good.